Hello. Hello.
Great question. I did. It's
Oh,
not going to be the
gross.
same number
Hold on. Sorry.
as before as for
Oh,
23.
weird.
Yes, it will be.
Sorry.
Good point. So
Hey.
I guess that helps with yes.
Hey, I don't know if you can hear that. I can. Can you? Hello. Hello. Oh, thank you. Okay. Hello, Steve. And does that? Hello. Hello. Okay. Hello. Hello. Were you hearing the craziness? Not that craziness. A different crazy. Well, anyway. Okay. Hello. Okay. I mean, okay. 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 We're going to do one more. Wait, but you can hear me, right? That's what the hello. I hear you is the question. Actually, can I hear you? Can you say something? Can one of you say? Oh, maybe I can't. Should I talk to myself?
Hello?
Hello.
Thank you. Okay, thank you very much. Okay, so I can hear you. Okay, and that's points right there. Okay, a couple things. So we're going to keep doing physics. I mean, I'm going to do this one more. There's this one more problem in the practice test. We're going to solve it together. And I've been using this as an excuse to not give you a test. I mean, for good or for bad. But I also know that that's and there's not so. A couple things to get out of the way since I know Thanksgiving, everything like that. What I think is, and I really do just want to focus as much in our limited time. I want to as much to be about physics as possible, and as little about like grades and stuff as possible. And I'm sort of trying to have us not have to do that much outside of our time is part of what it is. But I know we have to have this exam. So what I'm trying to get at right now is I'm going to get back to solving this gravity problem, to teaching you this gravity thing that you do need to know, and helping you solve this problem helping us solve this problem in the practice exam. Then we have to bite the bullet or I have to bite the bullet and like have an exam of some sort, and we're going to have a final exam. The thing is, what I want to do, and I'll propose, and I know we've had a proposal before, and then I just walked away from it, but to be as clear as possible, when we're done with this gravity problem going over here, the exam you're going to have is basically going to be, I think, these three problems, like the one that you first sort of voted for or whatever, or asked me about, and we went over. And then we went over the next one, I think, by my recommendation, because I thought it was relevant to what we done. And then we're doing this one by my recommendation. But I'm going to say, like, that's going to be the exam, like, for real. And even more than usual, even more than I did in 203 last semester or whatever, I'm even going to say right now that once we agree that that's the exam, and I won't flake out again on it, hopefully, and once we take it, I'm going to tell you that it really is going to be the exam. Like, I'm going to put even less surprises or variations for 1,000 reasons. In other words, we're going to do the cheating, so to speak, in advance, even more than usual. What you're going to turn into me is your best possible version of solutions to these three problems that we're all doing together right now. In other words, it's going to be an enormous reward for anybody who really has been paying attention to what we've been doing together. You're not going to have to like invent any real new wheel, okay? But I'm also going to, and so you're going to know in advance exactly what it's going to be, and then you're going to do it at home, and then you're going to turn it into me. And so the whole thing is going to be, even though I've maybe said this before, is like, it's not going to be about who can find out the solution to this problem, like on the web or whatever, and therefore, save themselves heartache that way or get an advantage that way. I'm telling you in advance what the questions are going to be, and I'm giving you the answers in advance. So what it's really going to be, if you like, if tests are contests, or if exams are contests or competitions of any kind, your contest is to be able to write down all the solutions to the problems, like in a manner that shows as much as possible that this is the result of you having been paying attention and taking these notes and following these problems. In other words, you're going to show that you really, really understand this crap that we're talking about in class. And it's not going to be about surprising anybody with what is the answer to this question. It's, can you show me the answers in as deep and impersonal a way as possible, like with as most pictures as possible, or as much explanation in English, or if you're better with pictures, more pictures. If you're, like wherever your strength is, you're gonna, and I'm gonna stop talking about it in a second, but I'm saying again, like, I think what the exam's gonna be is really gonna be these three problems, and you're gonna have nights to do them, and then you're gonna turn them in almost so it's like super decorated, super personally neat and clear homework, if you like, is what your exam is. And you want to make it as easy as possible for me to grade and as hard as possible for me to find anything wrong with. Like, you're just going to show me that you really get it. That all said, I'm saying this because I know I'm stressing people out with like having that exam just linger like this. I'm going to suggest that in the back of your mind, while we continue to do the physics today, while we finish that problem, knowing that that's what the exam will be. Again, it's those 3 problems, the one, and I might not even change the numbers. Like, that's how like stupid I'm being in a way. It might, I mean, it'll be a different copy, so you know you're looking at the right document, but I might not even change the numbers, but it'll be those 3 problems, like the third one being the one that we're in the middle of right now about gravity. I'm proposing to everybody that you consider the possibility that that I post this thing on Monday and you turn it back to me at the last minute before we go away to Thanksgiving, which I think is, in other words, I know Wednesday is Friday and it's not actually a class day for us, but I'm proposing something like I post it Monday and you return it Wednesday before Thanksgiving, or I post it Friday, like tomorrow if you want, and you'll tell me, but like we should knock it out before Thanksgiving. But again, I'm telling you what it is. It's these 3 problems. So that said, I'll give you time to think about it, how best to do this or whatever. But I'm going to continue going over the gravity problem. Oh, and one last thing, as far as your grades also, just remember, there is a thing that I can base grades. Like, I could give grades right now for the end of the semester if I had to, right? If like every school shut down and everything and we didn't have, I could give you grades based on all these points that you are collecting in class and that I'm giving back. Like, if I had, and again, I don't have a problem with everybody getting an A. So I could even literally say everybody has at least 40 points or whatever gets an A or something like that. But I want to continue that going, that point thing. I think it's working for people, or when I do it, I think it's working. So you'll notice in the Google Classroom, you got a few more of those points assignments today, like different point values for different things. If you submit, I don't want to over talk it, but if you look in those portals, you'll see, yes, as usual, just if you say anything, keep a record of it, write it in whatever day, and you get 50 points for that and you get it back. But I'm also adding, like, if you put in a JPEG or something, if you write something, if you take the risk of making like a little diagram or solving something for us, and you have the guts, which I really do think takes guts, to like put it in the chat or somehow share it so that possibly we all end up looking at it, submit that, that's 75 points. I may have mentioned this before. There's other things like that I just put in. You can look at them at your leisure. It don't have to be today. Just like when you do so, or if you actually use your voice, as opposed to putting in the chat, I'm saying that's a bonus 75 points. Again, you can, whatever you do, you can always put in for the regular 50 points. But if you actually use your voice, I'm saying it's 75 points. Also, but here's the best one though. I'm very proud of this. I put in one, I think it's called like assignment 17 or something, or 14. I put in one just today that I'm dead serious about. This one's worth up to 80 points. This one, you keep track on your own. If you say 4 things in class today and you in your heart believe they were all, even if someone else said 3 of them, whatever, but you like put 4 answers in the chat or something like that, or just did 4 or asked 4 questions, blah, blah, you write each one of them down on the piece of paper, say this is 4. I think I deserve 10 points for each one of them. Write a big 40 in a circle on the piece of paper, submit it. I'll check, like you are saying to me, don't you remember when I did these 4 things? Right? I mean, that you're testifying to that, but I'll look and be like, oh yeah, I totally remember that. Oh yeah, okay, 40 points, good. Like, you keep track. If you do 5 things in a day, write the 5 things down and tell me, I think that's 50 points, Yaverbaum. Like, challenge me. Like, do you not remember this, Yaverbaum? And I do have a good memory. So I'll be like, yeah, okay. And so we could do that to any number of points, but I'm saying you can even keep track. You could say 4 things. If you write them all down and you remind me, it's 40 points. Okay. And I'm going to try to do, just to keep it, and you be the judge of whether you think it doesn't matter if someone else said the same thing or not, or if you said it fast or not, blah, blah, blah. Okay. So try to just keep that buzz going of people. And again, just remember, so then we're going to have an exam because we have to have an exam, but don't think of the exam as like your, sorry. Oh, okay. Yeah. Oh, okay. Yeah. Oh, fine. Oh, fine. That's totally fair and helpful and gutsy. That's totally, wait. Okay. Yeah, no, in fact, I think it's, sure. And I will let sort of, again, oh, okay. Then I will let, fair enough. And I apologize for, wow, I knew there was a reason I like this class. Okay, then, let's say, and I've been, that's fine. If that's best, I will say, wait, today is Thursday, tomorrow is this weekend, in fact. Okay, because I don't want to break another promise. And I'll put this in writing in a second. Like, and I'll also give time, like, I hope everybody understands what's happening here. This is like true, it's clearly not democracy. I'm not pretending this is democracy, but it's also not dictatorship. But it's also not majority or like, this is just like the louder voices are going to carry the day in a way. Not because I want to punish quiet people, but I do want to reward the gut. So I will put this, by the time of class is over, I'll put in writing in your Google Stream that I won't falsely promise that you'll have it in your possession tonight. I won't, because that I might screw up. But I can promise you right now, assuming that the rest of the class kind of like confirms this by the end of today, I will promise that I'll have the exam posted by tomorrow night, because tomorrow's right. And then you could turn it in by Wednesday. Yes, like you can have as long as you want to have it, but if you want it earlier, and I think that's what these guys are saying, just to translate to the rest of the group, they're saying they want me to hop to and give you the test as early as possible, because then the earlier I give it, still they'll have the more time to do it. And I agree with that. Like, you're right, this is a take-home thing. So getting it in your possession earlier doesn't have to mean for some of you that your clock has to start. You understand what I'm saying? Okay, so I will promise that I'll get this exam posted to you by tomorrow night. Again, and I apologize for taking so long. And when I say this exam, I mean the 3 problems, the last of which we'll finish solving right now. There's still time for other people in the class to weigh in. It's not meant to be a race like this. Like, I'm going to start talking again about physics, but if other people, in 10 minutes are thinking more about what these guys said, or I don't know if you guys private chat among yourselves, I don't know, but like whatever, I'm not shutting this down, but just in fact, okay, great. No, I think that's very cool. And let's even put it this way, when 10 minutes left in class with 10, it's right. Assuming I'm not correct, assuming I'm right about the time, if class ends at 1:30, right, I would totally welcome, I would ask, in fact, say around 1:15 or so, one of you just remind me in the public thing around 1:15, say, please confirm the test posting, which would mean to me that I would put at that, because obviously not everybody's paying attention in every moment, but I'll give till 1:15 for everybody to notice this. And at 1:15 or so, I'll put in the Google Stream the declaration that the test will be posted tomorrow night, which probably means like 5 p.m. Because you don't have that, right, at 5 p.m. And I'm assuming, and we'll say, we'll say it's due Wednesday. Yeah, although we do have class. Can you just confirm one thing, you guys? We do have class this Tuesday, right?
Yeah, we have class on Tuesday, just not on Wednesday.
It's not on Wednesday, right? All right. So let me just think that the one part I have to think about is exactly how that works. Like, if we meet in class in the middle of all this exams out there, that might be weird, but I'll just think about that. But all right, just remind me at 1. And thanks, by the way, that counted as a voice. Voice. Okay. So
I was saying, like, if anything for Tuesday, the start of class. If anything for Tuesday, we could also use it as like, if we needed your help with any last minute parts on the exam. So like, we might have, if only to be like, okay, we're still working on it, but we have a question about this, like,
actually,
more so like something like that, if that makes sense.
No, it makes total sense. I'm saying no because yes, I mean yes. No, that makes total sense, and it's the least I could do. You're right. And then yes, you're absolutely right. All right. So let's say, I don't know why, I don't usually do it that way, but I don't usually do anything, and I don't usually have a virus. Yeah. So yes. Okay. So that's what I'm saying to everybody, and thank you again, Nick. And to everybody, that's 75 points right there, not to be weird. And all of you, all this input that's going into this stuff, right? This is just as real as physics or more. So, all right. So I'm pledging based on like the feedback, based on that, we're saying that at 1:15, someone will remind me to put in the Google Stream. Tomorrow night at like 5 p.m., I'll put the exam in the Google assignment stream. You will have till Wednesday at some time to actually turn it around and get it back. Like, it will count as an exam, but it's like an assignment in that you do it your way at home, PDF, blah, blah, blah. You'll turn it in by Wednesday. And as Nikki just to confirm again, what I'm like, the written confirmation comes at 1:15, but I'm just vocally, because I know this got flaky. So what Nikki also just said also applies. That is, we'll still meet as a class on Tuesday. I'll be doing other physics, at that point. Like, I won't be reviewing this anymore or anything. But right, if any questions come up of any kind, the worst thing I could do is say I can't answer that. But especially, right, if anybody's having any difficulty or anything, it probably would be good for me to know and for you to have a last opportunity for us all to correct course. So yes, that's perfect. And then we'll have it done before we go away Thanksgiving. Okay, that's great. I appreciate that everybody's working with me. Oh, and what? Oh, okay. Now, right. Yes. Now, thank you. And it's funny that I thought I had done this a long time ago too, in terms of what Steven's asking in the chat. Again, many, many points. All of these assignments, right. So I posted 11 through 15. And in fact, one of them, I think, had a crazy name like 17. There was a miscount I have to change. But all these game assignments, for some reason, they were really working with you guys, and then I lapsed in putting them in. But any one of these game assignments, each one of them really is like a portal. This is important to everybody because this was causing confusion in the other classes too. And this can work really well if we all actually get it. Each one, any assignment portal that I ever put in from now till Christmas, if it's called the game Take Anything, then it's a total optional thing. You can leave any of them alone. Any of you can. You can like not turn one in, and you definitely don't get a 0 or anything like that. You can also turn them in whenever. They're like coupons or something that apply to any class period you want. Like in principle, I've been throwing them out at you like at various classes, but they're all optional. It's just that any one that you think you could ever apply, you should. Because they're all just free points. So like any one of you, particularly say Stephen, like he just asked a question in the chat, right? So he definitely should take, and this is to everybody, this is like really where you're going to build, this is like the way to build a grade that is safe and secure even outside the exam, which hopefully is not meant to be stressful. But again, like this is where we want to build mounts of data that say we actually did take this class. Say Stephen looks at the first, assignment, take 11 or whatever, and it just has random instructions that say submit a PDF of any comment you made, blah, blah, for 50 points. Okay, he's asked this question, so he should totally use that on a piece of paper. She'd write down, like, I asked that question about, do we have to assign, respond to all of them, whatever. And he just reminds me of that, submits the PDF of it, and I see it, and I'm like, oh yeah, I remember, okay, great. And I just write great, and he's got 50 points for that. But now the other ones are like specialized things. Like one of them says, if you actually can phrase a question to me as a multiple choice, like if you can literally ask me a question that limits me to yes or no, or true or false, or wait, do we use sine or cosine, or that? If anybody does that, then not only have they made a comment that they can already submit for the 50 points, like the Stephen example just now, but I'm saying also, if your comment fits that particular characteristic, submit it again in this other portal for the additional 75 points or whatever. Or if someone puts a JPEG in the chat, they should first and foremost just submit that like record of that for 50 points. And I'm just saying, just a reminder to me, don't you remember I put in it, like you don't even necessarily have to screenshot it, just remind me. But if they did a JPEG, the assignment portal that's called like a picture is worth 1,000 words or whatever, they should also use that. These are like bins of points that you can apply, that I'm asking all of you, I'm encouraging you, anything you do, in other words, that shows that you're alive during this Zoom class. And some of you do a lot of things like that. And in fact, many of you do a lot of different things to show you're alive. And it always sort of blows my mind that you can or do. But I'm trying to give like different point values to different ways that you can all show that you're alive. And I'm saying anything that any of you applies, it's like Google labels or whatever. They're like labels, not, so anything that you think applies, like use it wherever it applies and just collect those points. It's just points to reward. They're like Nook miles in Animal Crossing, if anybody plays that. That's actually where I got the idea. I'm just literally giving you Nook miles for like any freaking thing that I think is good. Barely alive. Okay, I think, oh, sorry. Oh, yeah. And let me say, so I'm looking at the, and this is all we're, oh wait, great. Let me see if that, oh yeah, okay, so no, I'm just catching up on the chat now. Like if I were a student, I would give me points for like, when you remember to read the chat, professor, give yourself 10 points. Like, it's like that kind of thing, but it really is worth everybody understanding this, because this is my totally cheap, dumb way to just keep us all buzzing and keep us all alive while we're here. And also, the more we do this stuff, the more I feel like I know you guys from these conversations here, even when I keep postponing tests or this or that, then the more we all like know we're actually learning physics and deserving grades from what, good grades, I mean A's, from like what we're doing here, and the less we often get freaked out about what we're supposed to be doing between classes, because I think that's hard for everybody to manage, certainly including me. So anyway, to make this point thing clear, that like Stephen's asking me about in there, and other people are asking about in the private chat. First of all, some of them, if you turn them in, I haven't turned them all back yet. Like, they are easy to turn back. That's what I like about this too. Like, once I do them in piles, you should be getting some stuff back from me, but you will get, like, if you turn one of them in, you'll eventually get just like a word or something from me that says like, yes, I remember. And then you'll see the points recorded. And that's your record that you know that the points are going in my book. So even if you didn't do some from a couple of weeks ago, but now you understand, then just do those, like any ones you find, because it's going into a computer. It won't double count, and if you lost one or you think I never turned it back, you could turn it in again. Like, I mean, I don't think I actually lose them, but if that makes any sense what I'm saying to anybody. But the best one of all is the one I just put in today, and I'm dead serious about this. I'm saying from here on in, if you're catching what I'm saying, you can fricking just do stuff in this class. You could submit a JPEG to the chat, or you could say something out loud. You could make a joke even, like about my mother. No, leave my mother out of it. But like anybody, or just like Nikki, you know, she took the mantle and granted, I just like didn't even give anybody the opportunity to vote or anything, but Nikki took the mantle and did the Zoom thing when I wasn't there. Like anything like that, you should give yourself points for. So one thing I just put in the thing was like, write down everything you think was worth 10 points. Each thing you did, to give yourself 10 points for each thing. And I'll verify, like you are looking me in the eye and saying, I did this thing, Yaverbaum. You remember I did. So you obviously don't want to like lie and say you ran the whole Zoom show if I know you didn't. But I'm saying if you make 4 comments today, put it in that thing for 40 points. I've said enough about this, but it's a Nook Miles thing. If you, okay, barely alive. Does that mean, I think that means what I think that means. Okay, I'm gonna go on with physics. Well, I luckily just happen to have some physics in my hand right here. So I'm saying this now. Okay, I'm turning the page. Well, we're talking about gravity here, okay? And this is all in the context of that last problem in the practice exam, which I'll go back to that screen at some point, but I'm talking about gravity. And I'm reminding you of the equation that in theory is from last year, but who knows, or last semester, but it's supposed to be the inner mathematical workings of the force that automatically exists between any 2 masses, points of mass in the world. Okay, now remember a force, I think I said this, remember a force always is a push or a pull between any 2 objects in the world. Like for there to be a force, there always has to be 2 points of mass or 2 objects, things of mass interacting. But most forces involve 2 objects touching each other. In fact, all mechanical forces that we know, all mechanical forces like the normal force, friction force, the tension in a string, all the forces we deal with mechanics are all pushes and pulls between 2 objects, but they're all readily identifiable by the presence of physical contact other than gravity. Gravity is its own thing precisely for this reason that gravity does not is an interaction between 2 objects always, like any force is, but it is a non-contact interaction. In fact, it's called action at a distance, kind of like our learning right now. But it's called action at a distance because it involves 2 objects being able to pull each other without touching at all. And the reason that's such a heavy insight, the reason it's like so weird that we would believe in that or think that we can make any sense out of one object pulling on another without touching it is, if you can pull another object without touching, that means you don't have to do anything to initiate this pull, right? If gravity is a pull that is exerted by one mass on another mass through a distance across empty space without touching, then that means gravity is always happening. It means the first object doesn't have to do anything, doesn't have to perform any action or take any initiative or like bring rise any kind of event in order to bring this force into existence. If the mass exists, the force automatically exists, is what we seem to be saying about gravity. And that's a crazy thing. Like, I mean, who knows why that is? I mean, we have ideas, but the first thing we're just saying right now is, okay, given any 2 points of mass anywhere in the world separated by distance r, they're going to automatically pull on each other with, with a force vector whose magnitude is given by this equation right here, okay? And the equation says the bigger either mass is, the heavier the stronger the force, the stronger the pull, and the farther apart they are, the weaker the pull, right? Like the r is in the denominator, and in a very big way, like the r is not only in the denominator, but it's even squared. So like the farther away you are, really the force gets weaker and weaker, like very rapidly, the farther and farther you get. But that's the equation. That's the nature of the gravitational pull that automatically is exerted by any one point of mass onto any and every other point of mass automatically all the time. So this is existing between any and every pair of any 2 points you can think of, right? Like right now, an electron in the breast pocket of my shirt is pulling on like a piece of like iron dust in the 3rd planet revolving around the star Alpha Centauri or so, like, right? Like every particle everywhere in the universe is pulling on every particle according to this equation. Okay, fine. But then that means, okay, that means that gravity is like happening everywhere. When we want to start applying gravity to like planets or stars or moons, what we have to do is actually add up the effects of this equation over and over and over and over again. In other words, it's not that the Earth actually pulls on me, it's that all the little bits of Earth all together simultaneously are pulling on all the little bits of me. That's how gravity works. So to look at anything complex, we're going to have to start adding up each individual pair of particles. And that's going to take a long time unless we assume that space is symmetric, that we assume that like whatever happens on the x-axis also happens on the y-axis and on the z, and we start assuming that we can take advantage of cancellations and stuff like that. So in other words, what I'm saying is, let's look at case one of gravity. This is all, I'm explaining gravity here in order, again, this all goes back to the gravity problem in the midterm, but anyway, I'm explaining something. I'm saying, let's imagine that we have some bit of mass, some little bit of mass, call it lowercase m2. Like I'm focusing my attention on this little bit of mass here. And I want to know how it's being pulled gravitationally by some other mass in the universe. All right, so if there's mass 1 above it, this dot right here, it's going to pull on this mass according to the equation. And it's a vector equation. Gravity is a force. The force is determined by the displacement between two objects. Displacement. Force is a vector and displacement is a vector. This is all about vectors. So if m2 is this little mass that I'm looking at, that I'm wondering about, and it's being pulled by this m1, the m1 above it, if it's being pulled by that black m1, then it'll be pulled up a certain amount. How much amount? GMM over r squared amount. Okay, fine. But what I want to make clear is that then if I come along, and that's all the equation says, it's like how two dots of mass will affect each other. It's an elemental kind of equation. But now if I come along and put in another dot, if I put in M1, like you could say M3 or something, but if I put in another M1, another source of gravity, another object that's going to pull, if I do the simple thing, if I just take baby steps and I put this M1 an equal distance r below the original lowercase particle M2, right? So I have no tricks up my sleeve. I've got a little planet called M1 sitting here, and I've got a sun above it over there pulling on it gravitationally. But now I put another sun underneath the same distance away, and like literally, you know, but an opposite direction away. Then the net gravitational force on M2 is literally that, the net gravitational force. It's the sum of gravitational force from 1 plus gravitational force from 2, the forces superposed, just as you would expect, because force is a vector, vectors add vectorially. So actually, I'm going to pause and ask now, anybody who wants to answer in any way, this is not meant to be a trick, but just to make sure we're all on the same page, before I like bore myself to tears. If we have literally this situation where we have M2 sitting there being surrounded by two identical M1s, like they're the same mass and they're the same distance away, but on opposite sides of M2, what's the net gravitational force acting on, what's the net gravitation? Oh, I actually even wrote the answer on the board, but I'll still be interested if anybody, so the answer is actually there. Yes, thank you. Yes, yes. And now that is total points. Thank you. And you see, then 3 people, 5. Oh my God, the chat has like the number 5. Oh, this is like, you know, I hate those icon badges usually, but wow. Oh my God, this is like so exciting. I'm going to screenshot this right now. Just this screen that of course doesn't look at all like yours because I can't control it, but my screen right now has like my dumb diagram on it, has like a bunch of like frozen faces that are, some of which are real people, but are all frozen. And then there's Steven's picture. Right, no, I'm in a bunch of black boxes, but then it has the chat right in front with like, boom, Robert, Yovelis, Casey, Durkel, Brianna, like, boom, all zero, you know, and you might think that is just, but that warms the cockle. I'm not even gonna finish my sentence. It warms the cockles of my heart, as disgusting as that sounds. And each one of you, that's total points right there, thank you. But yes, and I'm assuming that not only did that they're right. Like, just to be clear, forces superpose. The whole is the sum of its parts. It's, in a way, I'm trying to make it seem like it's, and here is an obvious example of it acting in an obvious way, that like the sum of the forces is the force sum. But just for the record, the reason this is an important point, you're going to see, we're going to apply this. I'm saying that this example, the thing that like 6 people, and by the way, even if someone right now while I was talking, even if some fresh person now just tuned in and typed in the thing 0, I want everybody to know that they would get points, right? And like, there's even that scenario where someone could be really diabolical and like literally just type 0 just because I just said that, and they still have no idea what the 0 corresponds to at all, but they could still do, and they could still do that. And then they would submit that to me, and they, in their conscience, would have a conversation about that, and I would eavesdrop, and we'd all go to hell. All right, moving on. What I'm saying that's important about this 0 here is this. We're performing. This is an example of superposition. This is an example of where forces obey a principle called superposition. This is real. This is not a joke. Where forces are superposing, meaning that the whole net force is equal to the sum of its parts. Now, in other words, a northbound force plus a southbound force is going to equal no net force. Seems totally obvious, I hope, like maybe especially based on my picture and everything. But I do have to pause to say it's obvious in a way that forces do that, but it's not obvious. It's not actually obvious because not everything does that in physics or in life. Just to be clear for a second, if I can try, but I'm saying superposition of forces. Okay, not everything obeys superpositions. Not everything obeys superposition. Quick example, like I could say, oh, I can grade 5 papers in an hour, and Walters can say he can grade 10 papers in an hour. Let's assume that's true, which totally is not, but it is true that he would be faster. And then we can get in a room together and say, fine, I can grade 5 papers an hour and you can grade 10 papers an hour. So let's get together. And then you would think an hour later, we should have 15 papers graded. That would be the whole being equal to the sum of its parts. That would be if our grading rates obeyed superposition. But you see where this is going, probably, if you're paying attention. That's like not at all what happens. Generally speaking, with people like Walters and me, if we get together in a room, the fact that each other is in the room is going to affect our original rate. Like I have a rate of how fast I do things, and he has a rate. But if we're next to each other, those rates mix and they interact. In fact, as we'll talk, and probably we'll be much slower. We'll do a total of like 8 in an hour. But maybe if it was my wife and someone else, because they were together, they would help each other. And so it might be like constructive interference. In other words, the whole does not always equal the sum of its parts. It's totally plausible for there to be like an influence and an influence all acting on something, but the influence is to influence each other and the whole net result be something else. That often, and it will happen in this course in other areas of physics, but forces themselves apparently don't do this. Each force just acts the same way it would, whether the other forces are there or not. So each gravitational force does just act according to this equation that we have. So the whole sum gravitational force on some object is the superposition of yes, that is exactly what I mean. Yeah, I mean that the net G force is the sum of the individual G vector forces. That is exactly what I mean. That's great. And that's like, you totally should, you should say, I think that was worth 20 points. And hey, you can. And I'll verify it. And I'll be like, no, it wasn't. But no, I will. But no, that's a great question. Because again, if you look at Durkheim's question, the reason I'm going to keep trying to talk things in terms of points is like, if you're like me, you might even look at Durkheim's question and say like, he just like, what was that? That's like obvious. Like why, how does that even advance what Yaverbaum said? Or why didn't Yaverbaum say that 10 minutes ago or something? But like, that is exactly what I'm saying. And what I'm trying to say is as obvious or simple and clear as it sounds once it's written the way Durkheim wrote it, it's totally not an obvious thing. It needs to be said and written like that because not everything in physics actually does do this. We're going to see with waves, which is where we're going with all this, waves actually don't superpose this way. But yes, I'm saying that when you add gravitational forces, the forces add just like vectors. And the net result of all is one big vector. That is the vector sum of all the, absolutely spot on correct. Okay, so then what this then means, okay, to everybody now, I'm saying, if I just have like planet here and it's pulled over there by a sun, okay, it's pulled like that, and the sun by Newton's third law will be pulled also. But now if I put another sun over here on the other side, they're going to cancel each other and there'll be a net force of 0. But now I can start getting more and more complicated, right? Like I could start putting things all around and making pulls that don't always perfectly cancel out. So you can see how we start having to use superposition of forces, and we have to start using the symmetry of space to start. If we want to deal with anything, and this is the reality in physics, if we're going to deal with the gravity of anything realistic, like actually a moon or a planet or a sun, sorry, symmetry of space, we have to actually recognize that anything, it's not just like in chemistry, everything is made of molecules and then they're made of atoms, but we're really actually kind of we're like geometry, math guys here in physics. We're really saying everything is built of points. Like what we understand is how one point interacts with another, like for real, like an electron. So if we want to now start understanding how the Earth orbits the sun or something, we have to look at the Earth as a huge collection of lots and lots of points, all adding up these vectors to get one big vector. And sometimes, hopefully, if the shapes are nice and simple enough, we can see simple cancellations like in this one. But they're not always that simple. So for example, here's the next case. What I am saying though, and what Durkheim is clearly saying down at the bottom is, therefore, the net gravitational force acting on any one object, M2, is the sum of all the gravitational forces from all of the big M1s acting on it simultaneously. So for example, take this case right here on the next page. I just happen to have right here up my sleeve. Oh God, is this? Oh yeah, we got time, okay. Now again, I'm taking a liberty here as a teacher. I'm giving you some background that sometimes takes, this is all to support what you have to answer in that question about gravity. The more you understand everything I'm saying, the more you'll be able to say, you'll see how this explicitly relates shortly but again, that's why I'm rewarding people who are able to pay attention and slog through all this. But this is all still in service of the gravity problem in the midterm, but nonetheless, just suspend disbelief for a moment and bear with me. I'm saying here in this example, imagine, and this is like all over the web, this example, but it's hard. Imagine you have like a ring of mass, okay? A ring of like a big ring of mass. But I mean ring, like strictly speaking, I guess this is like a two-dimensional kind of thing, like a ring, like like a ring, like a finger ring, but really big in space, okay? And the whole thing is a total mass M, and let's say it has a radius of capital R. Okay, and no tricks up my sleeve again, like already this is going to make things complicated. So we're keeping it as simple as it can be. It's a ring of mass, like uniformly dense mass all the way around it. Like it doesn't get thicker somewhere and thinner, like no tricks. It's just a ring, okay? But it goes like perpendicular to the plane, what I'm trying to do with my finger. It like comes in and out of the plane of the board here, right? So then if you can imagine it, like it's like sticking out of the board and then coming back in. And imagine you put your point at the center of that ring and you draw a line perpendicular to the plane of the ring. So this line called Z that goes across the page to a little point mass M2, right? So this is the line Z that I'm talking about. This is Z, right? And so what I'm trying to say, and I don't know how better to, I'm sure some of you, maybe this is a case where if one of you wants to draw this just better, if you understand what I'm trying to say and you want to put a drawing of it, you have my deep encouragement, but the ring is supposedly coming like in and out of the page. And so then across the plane of the page is this Z. M2 is sitting there. And the question becomes like, okay, what's the gravitational effect of this whole mass ring on the particle M2, right? Now, hopefully people could see where, like, this is like imagining a bunch of suns I could have strung a bunch of beads all around in this ring, or a bunch of suns all the way around. And I want to know together how they're affecting a point over here. Well, there's some kind of cancellations that definitely happen for sure. Like this point up here is pulling to the right and up. This point down here is pulling to the right and down. I think it's fair to say that the up and the down will cancel those components, but they're both still pulling on M2 to the right. And if you think about every single point on this ring is pulling M2 on some kind of diagonal vector, each of which may have the same length, but is pointing in a slightly different direction. So this point M2 gets pulled by all of these masses, and together, and we're not going to do this right now, if you actually do an integral, and you add up all of these force vectors continuously, which we actually will do, but not right now, you find that they all will pull on M2. In other words, there's a lot of cancellations, but there isn't full cancellation. Like there is a net effect of this whole ring, and the net effect is that the whole ring will pull on M2 all as though it'll pull it towards the center of the ring. Like M2 the net effect is that M2 gets pulled this way. As you might expect, it gets pulled toward the center, even though there is no mass at the center, right? But the center of the whole ring becomes like the force destination for the M2, and the magnitude of that force isn't just GMM over Z squared, because there is nothing at Z, the answer becomes this. I'm telling you this as an example, and it sometimes I hold people responsible for this proof, and sometimes but right now what I'm just saying is, case one is we had one point pulling on another point gravitationally. Case two was we had 2 points pulling on a third point, and they canceled out, so we had a net force of 0. Now case three here is like a bunch of points distributed nicely and symmetrically around a point, just to show that, and this is like pretty simple, right? It's like a ring of mass. I'm not saying it's easy, but I'm saying it's simple. It's just like, oh, what if we collected a bunch of points into a kind of a very symmetric pattern? Well, that would all pull on a point over here in a very nice symmetric way, a way that we can calculate, in a way that we could even make sense of, but not an obvious simple way. Like it's not just GMM over R squared. It's this crazy thing, GMM over Z squared plus R squared to the 3/2, like blah, blah, blah. Okay, so in order to get the gravity from any kind of, so what I'm saying is, oh, well, okay, we're gonna go to the next example, and then you'll see how, oops, someone's in the waiting room, which I don't understand how that works at all, what it looks like to you, or why I'm sitting at the moment. Wouldn't it be great if all of physics were a Broadway musical without a virus? That would be great. Okay, I'm gonna shut up. I'm going back to what I'm saying here is that, this is like case two or application two of how the net gravitational force on some object works. And it's just, you don't have to memorize anything really of what I'm saying so far, except I'm just saying, notice, the more and more, if we're trying to figure out the gravity from an actual thing, an actual three-dimensional shape, like a planet or a star, we actually have to build up that thing from smaller elemental pieces, because all that gravity actually tells us is what's happening at the elemental level. Okay, so it requires deploying the symmetry of space and the superposition of forces in order to see how something large like a planet actually exerts gravity. Well, here's the result. So we imagined 1 point, we imagined 2 points, and we imagined like 3 points. Then I asked you to imagine a ring, and I'm sort of just asserting what the answer is here. We could prove it later if we want. But now if we imagine the thing that we really need for this problem, for the problem on the practice midterm, imagine now we're a spherical shell. Okay, this is where my drawing becomes a major, major liability. So again, if you possibly can visualize what I'm saying, or you can see it in a book or see it on the web, well, I actually ultimately have a really good picture for you. But if you want to draw a better picture and then share it, that's fantastic. But what I'm asking everybody what I'm asking everybody right now to picture is a shell, a spherical shell of mass m. Put another way, that's what I'm equivalently saying is picture a hollowed out sphere, a sphere that has some central portion of it hollowed out, right? So it's like picture the rind of an orange, or picture a tennis ball that doesn't have cork all the way through, or whatever they have inside. Picture that, and picture that the radius of this whole spherical shell is capital R, and picture capital R, and picture that the total mass of the whole thing is capital M. Okay, this all seems very obscure. It all probably seems very obscure, but bear with it because it is. But we're picturing now a shell, like a shell of mass m. And furthermore, because again, it's like a shell, so it could be very thin, or it could even be thick if you like as long as you have this hollowed out center of some kind. I don't care how thick or thin the shell is, but let's assume that the thickness is uniform, and let's assume that the shell is uniform. What do I mean by uniform? I really mean uniformly dense. What do I mean by that? I mean, for any 2 equal bits of volume, we will expect to find 2 equal bits of mass. Like, I'm literally saying that, and it's actually super important. Of course, I think everything I'm saying is important. But the assumption of this thing now, like, again, we're trying to build realistic shapes, but from simple shapes. That's what we're trying to do here. Because we want to apply gravity to reality. So each step we make of increased complexity, we're trying to guard ourselves and keep things as symmetric as we can, so that we can add up effects as easily as we can. So what we're picturing here is a uniformly dense spherical shell of mass. What does that actually mean in mathematical terms? It means that the ratio of mass to unit volume is a constant. That's what we're saying, right? So we're going to give a name to that constant. That's what's happening right here. So like, things are actually happening on this page. Partly I'm just we're just stating what our assumptions are, but we're also developing a notation for expressing those assumptions. And so here we're saying from now on, that's supposed to be, this symbol here is a lowercase rho. I mean, it's the Greek letter rho. It's the lowercase Greek letter rho. It's used in physics to stand for three-dimensional density of any kind. Three-dimensional density, stuff per unit volume. Sometimes in this class, that's going to mean charge per unit volume. Right now, it means mass per unit volume. It could be any amount of, but if you're talking about three-dimensional density, we use lowercase rho to mean that. And what I'm saying here is, for this case, we're going to assume that rho is a constant, like it doesn't change. So if you take any infinitesimal amount of mass and ask, any infinitesimal amount of volume, and you ask what infinitesimal amount of mass did I find in that volume, no matter what piece of volume you pick, you're always going to find the same piece wherever you are. The derivative, that ratio is a constant. We're saying, okay, we're calling that constant rho. That's an assumption of the problem. Now, given that, and I know I'm talking fast now just because, like, well, this is the situation to picture. Now, and we picture ourselves as, so that's a big source of mass now, right? Again, we've gone from a source mass being a point to the source mass being 2 points to the source mass being like a string of, like a ring of points surrounding us. Now we're talking about a whole sphere, like a spherical shell is surrounding us. Like that's, okay, that's like what I'm sort of in the third dimension now, and I'm this little particle, M2, at the center of, there's mass everywhere around me. I'm in the center of a hollowed out tennis ball or a hollowed out planet, whatever. What we find using the symmetry and the superposition of space, I really should stop and ask someone a question, but this is what we find is these three things. And I'm like asserting it that way. I mean, I actually have a video where this is all proven that I made that you can watch. It's like super fun, where I prove all this. I mean, I'm not the one that proved it. Newton is the one that proved it, but I might give you, anyway. What the thing that I'm saying here now mathematically, if you can, and the hardest thing is picturing these situations, and that is what's hard about physics. It's like actually physically picturing the thing that can really only express mathematically. But I'm asking you to picture like a hollowed out huge ball, and you're at the center of it. And we're asking how much gravity is pulling on you. Like, in other words, really, sorry. Yes, I think, hold on. Yeah. I can. So rho. You know what I'm trying to say. I'm going to do this by God, but very good question. And in fact, because that's a good. This is a totally important question, because I'm really going to use this thing in a moment in this proof. So totally fair. And in fact, since it's going to come, oh, okay, cool. No problem. I'm even going to put the usual reward of asking a question. I'm going to like punish it by saying more than anybody wants. But because this really is going to come up in other ways in the course and in physics, like, yeah, this is what I'm saying. But I'm backing up to say, when I learned about density in chemistry, you know, I always heard density is mass per volume. I mean, that's true. But really, that's a specific version of density. Density is stuff per space. In general, the concept of how dense things are is like how tightly packed in space they are. So in physics, actually, we actually distinguish between stuff per three-dimensional space versus stuff in a two-dimensional space versus stuff in a one-dimensional space. Just as long as, since Wayne is asking, I'm just going to say we'll need these for later anyway. I don't want to make this any worse, but in general, we use rho to mean unit mass per unit volume. We're going to use sigma, lowercase sigma, to mean unit mass per unit area. And we use a lambda, or sometimes a mu, to mean unit mass per unit length. Like this might make it, in other words, rho is the symbol for how tightly packed things are in some volume, some three-dimensional region of space. Sigma we're going to use for how tightly packed things are in a plate or a plane or like a sheet. And we'll use lambda and sometimes mu. And I'm talking about like in the next thing we do, like very soon. So this is a very fair, reasonable question. We're going to use lambda or sometimes mu to mean how tightly packed masses are in a line. And last thing I'm going to say, just to spit this all out right now, because it seems like clearly at least one person is hearing it. Now, also later on, we'll use these same symbols, physics, to mean amount of charge in a unit volume or amount of charge in a unit area or a unit charge in a unit length. Like in other words, in physics, density is just this big broad concept of ratio of stuff per space. And since it's a ratio, and again, I'm saying more than Rain asked for or needed, but I'm just using this as an excuse to say this because I would have to say it anyway. Any ratio at all in physics, like stuff per space, we always, in the limiting case, express as a derivative. Like in the limiting case of the ratio, it's a tiny bit of mass per tiny bit of volume. Looks confusing to people, but I just want to say this. I'm not saying, I'm literally answering Rain's question, or or trying to. I'm not asking anybody to take derivatives of densities. I'm actually secretly right now exploiting this opportunity. I'm taking Rain's good question to secretly try to show you something that escaped me for decades, which is that densities are derivatives unto themselves. If you ever, whatever you're holding in your mind as an understanding of a derivative, if you understand a derivative at all, like however you understand it, you often probably hopefully think of it as some kind of instantaneous rate of change, right? Like velocity is like a derivative. It's a rate because it's a ratio. All derivatives are ratios, right? Like rise per run, like displacement per time. All derivatives are ratios, but we often call them rates because they often have time in the denominator. This is like a total public service to everybody. I promise this is worth it. I promise. I would be saying this another day if I weren't saying it now. All derivatives are ratios, and we call them rates often because they often have time in the denominator. But they don't have to have time in the denominator. This is the public service part. A derivative could be any kind of ratio at all. And a lot of ratios we don't think of as rates, we just think of them as ratios. In other words, a derivative could be a ratio of something to time, like velocity and acceleration and other like rates, or a derivative could be a ratio of something per space, like mass per volume or mass per area or mass per length. And in those cases, we call the ratio a density. We don't call it a rate, but they're both derivatives. Densities and rates are both ratios. They can both be taken to the infinitesimal case, so they're both derivatives. I'm saying that to everybody, like Rain said, nothing wrong, she just asked the right question. But I'm saying this because you're gonna see these symbols all over the place. And in physics, if you ever don't get scared and ever think you're suddenly being confronted with a derivative and a density at the same time. A density is a derivative. A rate is also a derivative. A derivative is just a ratio. Now I'm going back to the program. Okay, good question. Did I mention good question? Good question. Points. Okay, but back to the so rho is three-dimensional density. Now what I'm going to tell everybody, oh my God, is that it's 110. What I'm going to tell you is that if you picture yourself in the center of a mass shell, the first thing to realize is something that I think you would all agree. Like I'm saying it directly because I think it makes sense, which is that if you're at the dead center, you know how much weight you have. Well, I should ask everybody, it says it right here. The amount of weight you have right at the center of like a hollowed out planet, the amount of weight you have at the center is 0, as you might expect, and you might expect for exactly the right reason. To say you have 0 weight, you might have a lot of mass, but you don't have any weight. You're not being pulled gravitationally anywhere because you're at the center. Where would you be pulled? Like if gravity is always a pull that pulls everything to the center, you're already there, so there's no down for you to go. I mean, maybe that's not a good reason, I don't know, but it actually is the reason. At the center, you'd be pulled well, put another way, everything that's pulling you that way would cancel out with everything that's pulling you down that way, and you'd go nowhere. I'm hoping that sort of makes sense, but that's conclusion number 1. The one that has like a 1 next to it. But then number two, going a little bit more maybe believable, maybe not, is if you go all the way outside, this whole thing, what I'm writing, this is important, these facts, I'm giving you above, they're technically their name if you want to look them up on the web. Again, I did make a video about this, but technically the thing that I'm writing here is, this is all called Newton's, or these are the three consequences of what's called Newton's shell theorem. Okay, it all seems so obscure, I know. It seems so obscure, it seems like I'm making it up for some reason. I'm really not. But the second part of the shell theorem is this, that if you go outside of the shell, and again, the shell represents like a step toward actually being able to compute what's going on with a full round thick planet, okay? If we have a shell, a spherical shell now, and we go way outside of it, so that our distance, lowercase r, our variable distance from the center, lowercase r, is greater than capital R. So that means I'm outside the radius of the shell, right? That's like my assumption, like I'm over here, right? Then the total gravitational effect of the whole shell is perhaps what you would expect. It turns out that everything cancels out super nicely so that it doesn't equal 0. We're not left with no gravitational pull, but we're left with a gravitational pull that's exactly identical to what would have happened if all of that mass were just concentrated at its center. In other words, I'm saying if here we're out, if we're over here, if we are over here, this distance r away, outside the whole shell, so that this bit of shell is pulling on us like that, but this bit of shell is pulling on us, that way even more, and this piece of shell is pulling on this whole, every bit of the shell is pulling on us right here where we're sitting. It turns out there will be a net pull for sure. We are going to get pulled toward the center of this whole thing, and we're going to get pulled with exactly the same strength and in exactly the same direction as though all of the mass were just concentrated right at the center. In other words, the pull on us will just literally be GMM over r squared, where lowercase r is just our distance from the center. So if you put all that mass in a big shell, it doesn't make any difference to us at all if we're outside it. It's as though everything is just happening at the center. That's kind of how we've always treated Earth up until now, like in physics 1 in our life. This might not surprise you at all that I'm saying it, and good if it doesn't. It does actually have to be proven. It actually isn't. But if it makes sense, good. All I'm saying so far is if you picture a shell, if you're at the center of it, it'll all cancel each other out to not pull you at all. If you're outside it, it'll all cancel out to leave over just the effects of all of that mass sitting at the center. But now the third thing I'm saying is the thing that really is the surprise, I think. Totally can be proven more than one way, but it's not something I would just expect. The third thing I'm saying, so now I'm on number 3 here, okay? And I'm saying it like there's no problem to solve here. There's about to be an application of this, and I see that it's 112. But this last one is saying the hardest thing of all. Well, it's saying if you're anywhere inside the shell, it's now saying this. It's saying still picture that shell. Ugh. Picture that uniformly dense shell of given constant radius, capital R. And again, it could have some thickness. It can, but whatever that thickness is, it's uniform. It's the same everywhere. What I'm saying now, what Newton's saying, the surprising thing, and there's no way really to say it, I'm going to say it, is say that you're a little bit of mass, M2, at this arbitrary position, this arbitrary variable independent position called lowercase r. If you're there, we're saying that the net gravitational force, I'm saying right now, the total net gravitational force acting on you at that particle from, the sum of all of the bits of mass, all composing that one big shell, the sum of the whole thing, the sum of all of their parts on you, and maybe you're expecting I'm going to say this, the whole effect becomes 0. Wherever you are, like, I think it's obvious, maybe not obvious, I think it's very easy to see if you're dead center, because whenever pulls you from above, pulls you from below, anything that pulls you from the right, pulls you equally to the left, you go nowhere. But I'm adding to that now. I'm saying, well, Newton is adding this and saying, yeah, but actually the cancellations are so subtle and so amazing that actually, even if you go to a random spot there, okay, what happens is, and I know we're going to wrap up soon, but what happens is if you go to a random spot, like here, then you got all this mass, like you've got this chunk of mass right here that's a certain distance away that's pulling on you like that. Now over on the other side, and please try to follow this, I'm saying like this, all this mass is pulling you that way. On the other side, there's this much bigger chunk of mass that's pulling you that way, right? A much bigger chunk of mass, but it's a chunk of mass that is also farther away from you than this original chunk of mass, right? If you can follow what I'm saying, it turns out, and we can show, we're under limited time now, but what's really weird is like for every chunk that pulls you down and to the left, you can find a chunk up and to the right that is bigger by precisely the right amount, by the same amount by which it is also farther away. And remember how gravity works. Gravity is stronger the bigger something is, but it's weaker the farther away something is. In fact, it's weaker as a function of the square of how far away you are. Well, it works out perfectly that this chunk here, you see this chunk here has more surface area and therefore more mass than this chunk here. And the surface area of a sphere is 4 pi r squared. So the surface area of this chunk is bigger in proportion to how far away it is squared. And gravity is weaker in proportion to how far away this thing is from the center squared. So crazily, turns out it's not actually crazy at all, but it is a really pleasant, nice surprise that what we're saying is well, I'm saying just that for if you're anywhere inside a shell, for every chunk of mass that pulls you in one direction, there's a chunk on the other side that is bigger in mass, but farther away by exactly the same factor, and that factor is the square of how far away it is. It's bigger in mass by a factor of r squared, and it is weaker in gravitational pull by a factor of r squared. So for every chunk that pulls you one way, there's a chunk that pulls you another way. And so no matter where you are in the shell, this is what I'm saying here now, and we're almost done with this, and I'm going to pause for a second. Yes, right, totally, thank you, exactly. I was just, yes. Okay, so I'm going to say this, and I'm going to post the thing, and then, what I'm saying here is the ultimate conclusion of this is, and but it's two pieces that we're now going to put together, and you'll see where it flies. We're saying, given any shell, if you're outside it, it pulls you as though it were just a dot at its own center. And if you're inside it, it pulls you all not at all. You're weightless. You're weightless anywhere inside a gravitational shell. With those 2 points, I'm going to do something mathematically to finish this problem. Believe it or not, you may or may not see where it's going. But yes, let me pause first to put the official thing in the Google thing because of the thing. And I really do appreciate how thingy you all are. Hold on 1 second. Oh my God, but why? Incompetents are us. Why? Oh, yes. Okay. Pardon me for a second. And I am watching. I don't talk to myself. No, I'm really not. And when I do talk to myself, I definitely don't interrupt or comment on my own discussion. I never do that, really. Or lie. I never lie at all. What did the... What? Sorry, can you guys, I'm about to put this, can you guys remind me when you have lab? It's not going to change it. I'm not going to change anything as it, but can you remind me when's your lab?
Our labs are on Wednesdays at like 5:55.
Oh, that's really good. Wait, that's when they start at 5:55? Oh my
Yeah,
God.
and they go till about 8:30.
Oh my
But
God.
it varies based on the day.
You don't want to have told me that part, but okay. But wait, oh, you actually,
It's fine. It's fine.
oh, but this Wednesday you don't have it because this Wednesday is Friday, is that correct?
Yeah.
Okay, so, okay, well, thank you, that's great. All right.
Oh, you have all markers. What are you doing?
Okay, you guys are gonna check this in 1 second. Okay, I've just posted, or I will have just posted something. It must be important because I wrote it in all capital letters. So I must be a total crazy person or a president or something. No offense. Some of my best friends are crazy people, and presidents, but not of countries. But you'll tell me, check if what I just wrote is what you guys think it should be. Well, I'm looking in the chat. What is it? All right, okay. And that's just the official declaration. Like, again, that's not the thing. The thing will be posted. We're saying this tomorrow by 5. And I'm saying by 5 because maybe I'll post it earlier, but I don't think so. But it'll be posted by 5 and then it'll be due back from you guys to me. And it'll have rules in it and stuff, but the rules will be do whatever you can to do this correctly. It'll be due back to me Wednesday for lab time for 5:55 as though you have, but even though you don't have lab, blah, blah. So could someone just confirm or deny if they see that in their Google stream now? Is it clear and correct? Yeah, okay, great. Thank you so much. All right, awesome. All right, so that's the, thank you very much for your patience with all that. Again, we're just trying to do this in a way that, yeah, that. So thank you. Now, I still have like 8 minutes. I do want to finish this problem, so, or at least the hardest part of it so that you can do it. If I were in your position right now, it would not be at all clear to me what I'm supposed to be doing with this information. But hopefully you are getting the information I'm saying, because here's where it all comes together. And I am watching the clock. I really am. What we now have present, and again, I'm just talking, like you'll have to go back and look at the problem and read it and see how to literally break, like how to break down your answers to the actual questions, but you will see once you look at it that I will have answered it. And the problem is asking us, the problem is asking us to picture now a uniform sphere. We're going all the way to the level now, like to the highest, to an actual realistic, actual solid sphere, like of mass, of like plum pudding. And it's asking us to picture, so it's like a total mass M, and I know I have to, a little bit quickly, I apologize. Although again, we still, I guess, could talk on Tuesday, but total mass M, total radius R, right? But now we're saying this thing is solid. It is solid, like plum pudding, solid mass everywhere. So we're saying again that the density, the three-dimensional density, the mass per unit volume, however you want to write it, you could write it as, I'm encouraging you to get used to it as a derivative, but if you don't like derivatives, blah, 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 it doesn't matter how you write it, it's mass per volume. And I'm saying whatever that is, that ratio is a constant everywhere, okay, very important. And what we're being asked here, and I am gonna try to do this quickly, what we're being asked here is now, imagine again, that you're at just some random location, lowercase r, please distinguish in your mind. Lowercase r is the independent variable under discussion here. It's like the variable displacement that some particle could be from the center of this whole arrangement. And this is like real, again, I almost feel apologetic how obscure this all may seem, but you got this big ball, this big planet, you're somewhere inside it, somewhere underground, under the surface, at a variable displacement called lowercase r, like that stands for how far away you're testing different positions from the center. Capital R is the given constant radius of the whole thing, okay? And the question being asked, the question which seems, again, out of nowhere is like, for this arrangement that we're being asked, what is the net gravitational force acting on you? You are that little particle, you know, M2, and you're being pulled in all directions by all the mass everywhere. Well, sorry, so we want to know what is the total net gravitational force exerted on you, the little particle, by the sum of all that M1? Okay, that's what's being asked. And that would be a very hard question to answer if we didn't just have this whole like yammer through that we just had, like, because again, you're being pulled now by every little dot of mass everywhere around you. There's stuff above your head, there's stuff below your feet, there's stuff to the left, to the right. It's all being pulled on, it's all pulling on you. And the question is, what's the net effect of all this? Of course, we're going to use some kind of symmetry or superposition to do that. I mean, but can we even, or is it too hard? Well, here's what we say. And I really am watching the clock because I really do. Please bear with me. I mean, I think we can get this conclusion by 1:30, but it is a big conclusion. We're going to say, oh, there's mass surrounding us everywhere. That's very complicated. But we know two cases. We already have done a couple of cases. And in fact, our complicated case right now could be viewed as a sum of some of the earlier cases. In other words, if we are, now bear with me, if we are somewhere amidst plum pudding, so to speak, we're somewhere within the interior of this solid mass. So there, again, you got to picture, there's like, sorry, here we are at some random location called R. We're like standing here in the middle. There's mass everywhere. So if you can picture that there's mass like above our head and there's mass below our feet, this diagram is getting horrendous. The key thing to picture is, wait a second, picture where we are. Like here is the center of the whole planet, but there we are at the star. So divide the entire region. This is the key thing. If you can follow this, you can follow everything. Divide the entire planet into two regions: an outer shell of all the mass that's above your head, and an inner core planet. So it's basically like what we had was a big basketball. Now picture it as a munchkin, like a donut hole at the center, surrounded by a big three-dimensional donut. That's what we're saying. Like there's a small planet, and then there's a shell around there. And the two regions are wherever you're standing, right here. In other words, picture, and I am watching the clock, picture a subplanet at R, right? Picture a subplanet at R, and we can even call that subplanet like M sub S. This is very subtle, it's an English point, but what we're saying is, if you picture wherever you're standing somewhere, well, then there's a whole planet below your feet, and there's a whole shell above your head. What's the significance of that? Well, those are the two cases that we know how to calculate already. In other words, all the stuff above your head is a big shell. There's a big shell, and you're just somewhere in its interior. It all superposes to 0. So then all that's left is the subplanet under your feet. So if you're somewhere in this big plum pudding, and the question that's being asked, and we have 3 minutes, the question that's being asked is, what's the net gravitational force acting on you from everywhere in this whole thing? Well, the answer is only whatever the net gravitational force is from everything under my feet. And that means the planet that I'm outside of. And that whole planet just acts as though it's a dot at its center. In other words, the inner planet, subplanet. In other words, we have 3 minutes. In other words, I am doing this fast, but I'm saying logically, really, the sum of since all the gravitational vectors all just add up as vectors, like Stephen or someone said right at the beginning, I'm saying add up all the stuff above our head, that makes 0. Add up all the stuff below our feet, oh, that makes F equals GMM over R squared from just that mass. So the total gravitational force that we want here is going to be equal to this, but we're just about done. And if you have to go and then watch the tape of this, but I'm going to finish this even if it goes a tiny bit over, and I'm really sorry. But I'm saying that the net gravitational force of the whole thing is the net gravitational force from just MS, the part underneath our feet. But what is that? I don't know. It depends on where we're standing. The farther out we stand, the bigger that MS is. What is MS? This is the part of, well, this goes to Rain's question about the density. I don't know how big that mass is. I can't express it in terms of knowns, except I can because I know the density is constant. I know that density is constant, so I know then whatever that mass is in the subplanet, whatever that is to the subvolume, must be equal to the total mass over the total. This is where it all comes full circle. And again, I'm watching time. I'm sorry, I'm going fast, but I'm saying I can figure. I'm looking. I'm about to finish the problem. I'm about to get the gravitational force, but I'm saying it is entirely only due to all the mass comprising that subplanet there. So now I'm solving for the mass of that subplanet. Bear with me. And again, if you have to go, just go, and I totally will understand, but then please watch this at the end. The subplanet, we're saying, is to the subvolume as the entire planet is to the entire volume. So in other words, ms is total m times total v times vs. Well, what are all these things? Well, total m was a given. That's the mass. Total volume is the, I'm going to say this. I would ask you guys, but since we're talking, is the volume of a sphere. The volume of a sphere, of a total sphere, is 4/3 pi r cubed. That's the volume of the total given sphere. I'm supposed to multiply this whole thing by the volume of the inner subsphere. In other words, 4/3 pi r cubed. That's very important if you're still with me. Like, so there's going to be a lot of cancellations right here, but not all cancellations. Like this cancels, this cancels, this cancels, this cancels, right? But what we're saying in the end, is then the m that I'm looking for is going to be this portion of the total m. I'm just about done. I know it's 1:30. I'm just about done. But what was the purpose of this? The purpose is this is now what I'm going to plug in. Like, that's an expression for the subplanet. It's just saying the farther out you're standing, the bigger the subplanet you're on. And you're only going to experience gravity from that subplanet. That's what it's saying. Everything above you is all canceling out. It's like a shell. But below your feet, the farther out you stand, the bigger a planet you're standing on in exactly this ratio. So now we're going to plug this back in. Again, I do apologize. I see, but we're going to plug this. I'll stop saying it. We plug in here. So we're saying that, oops, sorry. We're saying the net gravitational force that we're looking for is just, according to the equation, is the net gravitational force from that subplanet. Now we just got an expression for that subplanet. That's the work I was just doing now. So we're saying this. Right, I'm plugging in, okay, and we're just about done. I promise I'm plugging in. Lowercase r means the variable, the independent variable, how far away we are standing from the center of the whole arrangement. That's what lowercase r stands for here, whereas capital R is the given constant known radius of the original sphere that we're somewhere inside of, right? Lowercase r is the variable. Capital R is the constant. So these two lowercase r's they are referring to the same thing. So this cancels, okay? And we really are just about to, and I can go back to, and as soon as I'm done, like I'll say I'm done, and then everybody can go, but anybody wants to hang and ask questions or ask me to go back to the page, of course, I will do, I shouldn't say of course, but I will not go anywhere. But I know you guys have to go. But I'm saying, we're just about to, I'm saying this. This is what we just solved for. And now here's the punchline. This is why this is all worth, all of this is like, I know, completely out of nowhere, it seems, right? This is technically the answer. This is the answer to part A of that problem. If you look back at it, the whole long problem with all the reading about gravity, part A is asking for what is the expression of the net gravitational force as a function of lowercase r of distance. This is the answer right here. Okay, I mean, this is the answer. But now let me, if you've slogged this long and hard with me already to get here, here's why it's worth waiting for. Like, if this is the answer for the force, then the question asks a crazy thing. It asks how much time would it take, like a rock dropped at one edge of the earth? Like it says this whole thing about if you make and you have to read it. But it says this whole thing, if you carved a tunnel from one edge of the earth to the other edge of the earth and you dropped a rock in the tunnel, how long would it take to reach the other side? And that's a crazy question, because we could do F net equals ma, or we could say x equals 1 f at squared, or one of our old physics things. But according to this equation, the force of gravity would change every moment. Like what this equation is literally saying, and I know I am watching time, but it's literally saying that if you're at the center of the whole planet, you don't weigh anything. But as you get farther and farther from the center, your weight gets higher and higher and higher. Like if you're halfway out to the center, you weigh half as much as what you usually do. That's what this, and if you're a quarter way out to the center, you weigh a quarter of what you usually do. That's what this is saying. It's saying your F, the force of gravity on you, is directly proportional to your R, how far you are from the center. So then it asks, how much time would it take for you to get from one side to the other? If you were dropped in a tunnel, well, I mean, you could do x equals 1/2 at squared, but this seems to imply that the A would change every moment. So how are you possibly supposed to do this? And what does any of this have to do with the physics that we're doing? I would actually love to ask all you guys, but since it's 1:34, I'm going to have to tell you, and maybe you've already figured out, but what this all has to do with and how we can get time out of something like this crazy thing. And again, if you've already know, and you can put anything in the chat if you want right now, and I'll totally give you point. If you know where I'm going with this, feel free, or you can tell me right after. But where I'm going with this is I'm saying, oh my God, the reason we just did all this work is to find out that gravity inside the Earth acts this way. It looks like gravity exerts a force that is directly proportional to displacement with a negative sign. In other words, the force of gravity is negative times some bunch of constants times displacement. This is Hooke's law right here, is what I'm saying. I'm saying that if you drop, and I'm saying this quickly, I'll say it more on Tuesday, but this is just so that you can like do this thing and think about it. If you drop a rock in a tunnel that you carve across like the whole planet Earth, this like the solid sphere of Earth, the force of gravity is really strong at the edge of the tunnel, and the rock will start dropping with this really big force and this big acceleration and no speed at all. It'll start gaining speed, more and more speed. It'll be accelerating, but as it's dropping, the acceleration rate will actually drop. The force will actually get weaker, according to this math, which is just like something on a spring. As it gets closer to the equilibrium, the force on it gets weaker, the acceleration gets lower, even as its speed gets higher, right? Until it gets to the center and has maximum speed, but minimum acceleration. This thing is a spring. This means gravity acts exactly like a spring, even though there's no metal, there's no coil. And if you want to know anything about time, and this is the last thing, this literally says, so this says F equals negative constant. This is why this is all worth. It says this, it says, and R is like X, it's displacement variable. So put another way, we're saying this, and this is where I'm just going to do this. And thank you for, I know you guys are still here, it's crazy, but I'm saying we can go like this, then MA equals that, right? And we can say this. Right, and this, and one more step and I'll go back, but I'm saying we have our good old friend or whatever, or hated enemy. If you're really following the course and all that, you'll see that what we've arrived at here, all this crazy gravity long story is it turns out gravity acts like this. This is a spring. This is a harmonic oscillator. Right, and so, and is the last thing I'm going to write. So if you want to know how much time it takes for a rock to go to the other side of a gravitational tunnel, you really just want to know what the period of oscillation is. And so if you just plugged in the appropriate numbers for Earth, like the Earth's radius and Earth's mass, I'm just telling you, you would get that the entire period is like 84 minutes. And if you drop it, and so if you want to know how long it takes for a rock to get from one side of a tunnel to the other, one cut through an entire diameter of Earth, the rock would fall as though on a gravitational spring, like it would fall faster and faster and faster and faster, but with lower and lower and lower acceleration until it got to the center and it was weightless, no acceleration. And then it would build up acceleration more and more as it lost and lost and lost speed until it got to the other. And the whole thing would take 42 minutes. That's 42 minutes to go one side, 84 to go back the other way. The whole thing would be 42 minutes. That's the answer. And that's because actually we can show mathematically that gravity in this case acts like a harmonic oscillator. That's the point of the whole thing. I held everybody 10 minutes over. I totally apologize. I owe you 10 minutes. Now I'm going to stop for any questions. You guys can totally go. I have nothing more. I'm sorry. Thank you. But anything you want to ask or anything, I'm here. I'm not going anywhere. I can turn back the pages too or whatever. Yes, absolutely. I can. I like how one person just disappeared. Yes, absolutely. And we could, yes. Is this, And thank you. That's total points. You should totally, even just asking me to go back 2 pages, especially you're asking me after time, after 1:30, right? Submit that for 2 things of points. Like seriously, it's like no more else. But is this the right page that you wanted? Wait, Gabriella, wait. Is this? Oh no, it's fine. Wait, no, you tell me. There's nothing to be sorry. Which page do you want? This one. Yeah. Okay. Sure. And again, no problem. And I don't mean to be keeping people. I can explain anything anybody wants now that I've held you guys this long, but no, you should all just go or whatever. But again, if there was one word for I'm sorry and thank you, I would want to be able to say it to you guys all the time. And I would say nothing else. Yes, go back. Yes, like, sorry, that one. Is that right? And I can explain also, but yeah, is that, yes, okay. No problem. Anybody else? Oh, thank you. No, awesome. And again, anybody, thank you. I appreciate it. Sorry. Thanks. No, thank you. I'm sorry. Thank you. Seriously, you guys are and thank you for always being so super on time, Young Jung. I totally notice. Or early, whatever. I'll see. It's down to yeah, you guys are like the core. I hope you all do Prism, really. I hope you take care of this country. And also, I can go if you guys are waiting to talk to each other. I always forget this. If you guys want me to go and hand over the thing to one of you, that's fine too. Or no, okay.
Bye, Professor.
Okay. Thank you so much, really. Thank you. Should I be scared?